Chris, there are two things that children all learn about the ocean. The first is that it's blue, and the second is that it's salty, but that saltiness is not the same everywhere around the planet. Tell me about how it varies.
Okay, so what we're looking at here is we're looking at a map of the salinity, which is a measure of how much salt there is in the ocean. And this, because it's from satellite, it's just of the surface. And as you can see, as you indicated, the salinity is not the same. So the red areas, they show very salty areas.
So this is the Pacific Ocean here, and it's very, very salty across the middle, and less so over there.
And then when we get round to the Atlantic, we'll see that the Atlantic is in fact even saltier than the Pacific. We see that there are some blue areas near the coast, and they're often related to large rivers. So if we stop just in a few moments' time, we'll see where the Amazon outflow is coming out here.
So here we go, about here.
So if we stop here, then we can see the Amazon.
So this is the coast of South America here.
This is where the Amazon River is coming out from the South American continent. And you can see that the signature of that fresh water that comes from a river propagates virtually across the ocean, across the Atlantic Ocean.
And these are quite small changes in salinity, but the Atlantic generally is quite a salty ocean. We can see it's got these big red patches, and it only takes the Amazon's a huge river, but it takes a relatively small amount of fresh water to change the salinity across this huge area.
The thing is, we're looking at a satellite. So a satellite actually measures the salinity in the top 1 centimetre. So if you imagine that the Atlantic Ocean might be 6 kilometres deep, you're only looking at the top 1 centimetre. So the salinity obviously then varies down the water column as well as across the surface.
So there's this big 3-dimensional structure of salinity. Why should anyone care about salinity? Why do we care how salty the ocean is?
So the whole ocean moves for 2 reasons. Firstly, because the Earth's moving, but the thing that drives that is what's called the thermohaline circulation. Thermo, because of temperature, so temperature is the major driver, but also haline for salt. So the whole thing is driven by differences in density related to differences in density in the water caused by changes in temperature and the amount of salt. And as you said before, the actual variability of salinity in the oceans is actually pretty small.
So what's happening with the thermohaline circulation is that if water is colder or if it's saltier, it gets more dense, and so it's more likely to move downwards in the water column.
So the poles are kind of the classic example where in the winter you get sea ice forming. So the surface of the ocean actually freezes and you get preferential removal of salt. So that's called brine rejection. And what you find is you get very cold, salty, very dense water that sinks to the ocean floor and then might, so from the Antarctic, might then not be seen again until it rises in the northern hemisphere at some stage.
So the salinity of the ocean is important, and this is satellite data of salinity, but it's very noticeable. We've looked at a lot of satellite data on this course, and it's all beautifully smooth and it's got all of this detail, and it's quite noticeable that actually this map isn't like that. Tell me about why that is.
Okay, so we're actually looking at monthly data, so each time the image changes, that's related to one calendar month. We've been measuring temperature from space for somewhere in the region of 50 years. The first satellite to measure salinity on a continuous basis was launched in 2009 when ESA launched the SMOS, Soil Moisture Ocean Salinity. The whole difficulty with that is, in order to measure salinity at a spatial resolution that's actually useful for oceanographers, you need a very big antenna in space. And obviously to get a very big antenna in space, you need a very big rocket, and it's prohibitive. So SMOS is very innovative. It uses an interferometric sensor. So what that means is it has 69 separate radiometers measuring the radiation. It's similar to a radio telescope where you have, one telescope here, one telescope there, and you look up at the sky, and they are often L-band microwave, which is the same frequency as SMOS uses. Instead of looking upwards, SMOS satellite is in orbit and is looking down.
Even though it's quite crude, it's still a global picture of salinity over the ocean surface. What sort of things is this data used for? What can it help us predict, and what does it help us understand?
To be honest, when the satellite first went up, it wasn't even clear whether we could measure salinity from space. So the fact that you see the Amazon River is in itself a technical marvel, in my opinion. The fact that you see that the Atlantic is saltier than the Pacific, The fact that the tropics, where you might be able to see rainfall, or you do see rainfall from satellites. So as rain falls in the tropics, you end up with freshwater lenses on the surface of the ocean, and these are detectable in some occasions from satellites. So we can use it to look at river inputs, we can use it to look at potentially ocean circulation, although that is linked obviously to temperature as well. Yeah, so there were lots of opportunities of what we can use salinity from space for.
But tell me a little bit about the Nemo model and how this sort of data goes into a general ocean model of what the ocean is doing.
Okay, so at the moment, salinity is not assimilated. So assimilation is the process where observations and model are combined together, and you have a knowledge of the error in both, and so therefore if you have more certainty in your knowledge of, say, the model, then you will go with the results from the model. If you have more certainty on your observations, then you'll go more to the model. So clearly salinity would be useful to be assimilated. So a lot of operational models will already assimilate sea surface temperature from space, sea surface height from space, and obviously, you know, I have a slight bias. I want salinity to be incorporated because salinity, the satellites that measure salinity are not affected by clouds. So unlike infrared temperature measurements, which can't penetrate through clouds, doesn't matter if there's clouds over the Earth. The salinity satellites, because of the frequency they're operating at, will be able to see through that and still provide information about the location of perhaps ocean fronts or other ocean features.
So this process of assimilation is important because it means taking vast amount of observational data and then comparing that, feeding it into a computational model, which is your best understanding, and sort of checking them against each other, so you're using the best of all possible worlds to be able to forecast the future. So that's a crucial thing, this assimilation of data.
Yeah. So it may be that your numerical model is very good at getting an ocean front, for example, but it might not get the ocean front in the right location. So by assimilating observations, you can therefore get your ocean front in the correct location, and that might be really important.
And the deal about all this is that it's a new thing, it's a new type of satellite measurement. The satellite you mentioned is the SMOS, the first one to do it. But this is useful data. It's not just that satellites only measure the same parameters, you know, the altimetry and the temperature and the standard parameters. There are new things that are coming online and starting to be measured.
So the SMOS satellite, by its title, Soil Moisture Ocean Salinity, provides details about soil moisture. So it can say how much, you know, if an area is particularly dry or it's liable to flooding, then it can provide information like that. And actually soil moisture is really important for global ocean models. Because of the frequency it's operating at, it can also be used to measure the thickness of sea ice. So as the surface of the ocean freezes in either the Antarctic or the Arctic winter, it can actually assess the thickness of sea ice. You're basically getting three variables for the price of one. So SMOS was also joined in orbit by a joint American and Argentine satellite called Aquarius, which its focus was purely on measuring ocean salinity. And unfortunately that stopped working mid-2015. But NASA have also fairly recently launched the SMAP, which is Soil Moisture Active Passive. Unfortunately, it's no longer active because the radar failed on that, but it still has the potential to provide salinity at the order of a spatial resolution of 35 to 50 kilometres, something that, you know, 10 years ago just wasn't possible.
So salinity really is at the beginning of its journey as a satellite variable.
Yeah.
So it's still, there's a potential, it clearly could be useful.
It's really early days, and so I mean you can see in this that there's lots of white areas where there's no data. There's lots of kind of, particularly down here in the Southern Ocean, there's lots of features that don't look realistic, and it may be that, you know, we're not quite there with the algorithms, but, you know, as I said before, we've been measuring sea surface temperature for 50 years, we've been measuring sea surface salinity for 6 years.
Got some catching up to do.
And yeah, so come and ask me again in 45 years time or so. And firstly, if I'm still here, I'll be very happy, but secondly, I think the results will be much more useful.
Well, it'll be exciting to see what comes online in the next few years.
It certainly will be.